Okay, so we are going to look at lots of examples using the SUVAT, or the constant acceleration or motion formulae. So this is what hopefully you had a go at deriving yesterday. If you couldn't get them, that is absolutely fine. You don't need to derive them from each other. It's just useful to know where these equations come from. And effectively, you've got 5 different equations where one of the variables is missing. So if you've got 4 pieces of information or 3 pieces of information and one that you need to work out, there's always a formula that you can work that out with. So as a refresher, S is displacement, U is initial velocity, V is final velocity, T is time, and A is acceleration. So we're going to go through 6 examples today. The book has constant acceleration 1 and constant acceleration 2, and kind of just looks at these 2 formulae in the first chapter and then these formulae in the second. Now, I don't think that's the best way of doing them, so I've just bunged them all together. I haven't done them in the same order as the book. I've done one from the first section, one from the second, one from the first, one from the second, and so on. So it's in a slightly different order, which is why I provided you with the PowerPoint. I'm going to keep this to hand. You get this in your formula booklet, so you don't need to remember them. I remember most of them just because I've used them a lot. Don't remember this one because I very, very rarely use this one. This one doesn't seem to come up in a lot of problems. But they're there for you. So I am going to keep referring back to that, and I'm not going to just do it without. And I would never expect you guys to do it without the formulae. So, example number 1. A cyclist is travelling along a straight road. And I like to try and draw diagrams if I can. So I've got my straight road. She accelerates at a constant rate from a velocity of 4 meters per second to a velocity of 7.5 meters per second in 40 seconds. And I know that she accelerates because she tells me. So we often put a double arrow to show acceleration, just to imply that things are speeding up, and then it's the meters per second squared. So it says from a velocity, so I knew that was my U, to a velocity, so that's my V, 7.5, over a time of 40 seconds. So that's my diagram. It's useful to actually write it out like this too. So part A says find the distance she travels in these 40 seconds. So that means we're finding S. So we want to find S, and we're given U, V and T. So the formula I want is S equals U plus V over 2T. Now, you don't get marks for selecting the right formula all of the time. Sometimes you do, because you're given them. They don't tend to give you the marks. But I still think it's worth writing it out, just in case you make an error in the copying. So if you say, this is the formula I'm using, they go, okay, they've copied the formula wrong, but they've substituted into that formula right, so you might get marks that way. So S is equal to, so U, 4, plus V, 7.5, over 2, multiplied by 40. So we pop that in our calculator, and we get 230 metres. Part B, find her acceleration in these 40 seconds. Now, I could use S, because I've now worked it out, but the likelihood, well, not the likelihood, but there is a possibility that I've made an error here. So I should always use the ones that are in the question. So I need to find A, and I've got U, V, and T. So I'm going to use this one. V equals U plus AT. So 7.5 is equal to 4 plus 40 lots of A. So 80, 40 lots of A. So 3.5 is 40A. Therefore, A is 0.0875 metres per second squared. So having these in front of you makes the whole problem a lot more straightforward. So example number 2, and I'll use different colours just to make it clearer when I'm going between my examples. Example number 2, a particle is moving along a straight line from A to B. So a particle is moving along that straight line with a constant acceleration of 5 metres per second squared. The velocity of the particle at A is 3 metres per second in the direction of AB. So I know that I'm travelling that way, so that's my initial velocity. The velocity of the particle at B is 18 metres per second in the same direction. Find the distance from A to B. So I've got U, I've got V, I've got A, and it wants me to work out S. So I've got S, U, V, and A. Well, S, U, V, and A is V squared equals U squared plus 2AS. So 18 squared is equal to 3 squared plus 2 times by 5 times by S. So 18 squared equals 3 squared plus 10S. So we end up with 315 is equal to 10S. So therefore S is 31.5 metres. Now these first ones have been quite straightforward because our signs are all the same. So we're travelling in one direction, we're speeding up rather than decelerating. The velocity is moving in the same direction, so we haven't had to worry too much. As they get slightly harder, sometimes there is more for us to think about in terms of the signs in our problem. So example number 3, I'll just bend it there so it hopefully stays. A particle moves in a straight line from point A to point B with constant deceleration of 1.5. So it's decelerating. So that means our acceleration is negative 1.5 because it's slowing down. That's the only way we can differentiate that we're slowing down is by putting negative. The velocity of the particle at A is 8 metres per second. And the velocity of the particle at B is 2 metres per second. So because we've said that they're travelling in this direction, this must be the positive direction. The fact it's decelerating means it's negative. Find the time taken for the particle to move from A to B. So we have U, our initial velocity is 8 metres per second. Our final velocity is 2 metres per second. Our acceleration is negative 1.5 metres per second squared. And we want to work out how long that takes. So V, U, A and T, we have V equals U plus A, T. So 2 is equal to 8 minus 1.5 T. So negative 6 equal to negative 1.5 T. Now you can see why signs are important. If that had been a plus, it would have ended up with minus 6 equals 1.5 T and would have got a negative value for T, which obviously doesn't make sense. So T is therefore equal to 4 seconds. Part B. Find the distance A to B. So I've got U, I've got V, I've got A, and I need to work out S. So I'm going to use the S equals U plus V over 2T. So S is equal to 8 plus 2 over 2, multiplied by my answer for t. I do have to use it in this case, 4. I could use v squared equals u squared plus 2as, because that would use use the things that I'm being given in the question. But you could do this way as well. So s is 5 times 4, which is 20 metres. So I could have used v squared equals u squared plus 2as just to show it works. So 2 squared equals 8 squared minus 2 times 1.5, because it's the minus 1.5, times by s. So 4 is equal to 64 minus 3s. Therefore, s is 20 metres. So it works both ways. Okay. Part C and part D. So I'm going to draw what I'd already drawn. I apologise. I don't know if you can hear that. My cat is climbing over me at the moment because he's desperate for me to give him attention. And I'm not, because I'm doing this video. So he is not particularly impressed at the moment. But there we go. After reaching B, the particle continues to move along the straight line with a constant deceleration of 1.5. Getting lazy with my units now, but as long as when you write out the letters, that's fine. The particle is at the point C 6 seconds after passing through point A. So all of that takes 6 seconds. Now we worked out that that takes 4 seconds, so therefore B to C must take 2 seconds. So it says find the velocity of the particle at C. So it's up to us what we work out, whether we use this information or whether we use just this subpart of information. It might be best to use the whole thing, just in case we've made an error, with that being 4. So u is equal to 8 metres per second. T is equal to 6 seconds. Our acceleration is negative 1.5, and we need to find v. So v equals u plus at. So v is equal to 8 minus 1.5 times 6. So 1.5 times 6 is 9. So therefore our velocity is a negative 1 metres per second. So that means that at point C, they're actually travelling in the other direction. So what that might mean is that it's gone past C and come back, because all it says is that the particle is at point C 6 seconds after reaching point A. That doesn't mean it hit point C 6 seconds the first time. It probably means what the particle has done is it's gone past C and come back in 6 seconds for it to be travelling at negative 1 metres per second, because it means it's travelling back this way. D, find the distance A to C. So I'm going to use information that I've already got in my question. So I know that at A, I was travelling at 8 metres per second. I know my acceleration was negative 1.5. I can either use the fact that I know that my time was 6 seconds, which is obviously given to us in the question, so that might be useful. And then I need to find the displacement, which is the distance. Because where we're travelling in a straight line, it doesn't actually matter if it's gone past C and then come back, because all this information is just literally about A to C. So that will be the displacement from A to the distance. In this case, will be the same as the displacement, because it's not, it's all in the same direction from, C is in the same direction from A, as this all tells us. So we don't need to worry about distance being different to displacement in this case. So U, A, T and S, it's one we haven't used yet. S, A, U and T. S equals ut plus half at squared. So S is equal to 8 times 6 minus a half times 1.5 times by 6 squared. So S is equal to 48. A half times 3/2 is 3/4. 3/4 times 36 is, I believe, 27. I'm doing this in my head because I used a different formula the first time I went round. And that should be 21 metres. So the distance from A to C is 21 metres. Okay. Example number 4. A particle is moving in a straight horizontal line with a constant deceleration of 4 metres per second squared. At time t equals 0, the particle passes through a point O with a speed of 13 metres per second, travelling towards a point A where the distance OA is 20 metres. Find the time the particle passes through A. So we need to work out the time. We know the initial velocity is 13 metres per second. We know the acceleration. We know it's a deceleration, so it's negative 4 metres per second squared. And we know that the distance, so S, is 20 metres. S, U, A and T. S equals ut plus half at squared. So 20 is equal to 13t minus a half times 4 is 2t squared. So we've got 0 is equal to minus 2t squared plus 13t minus 20. Wonderful, we have a quadratic. So we can use the polynomial quadratic solver on our calculator. We should know how to use this. If you don't, send me a message and I'll show you. So what we get is that t is equal to 4 and t is equal to 2.5 seconds. It says find the times when the particle passes through, so that's great. But let's think what that actually means about the travelling of our particle, which I didn't, actually I can add it to the diagram. I'll just use a different colour. So what it means is that the particle did something like this. So it passed at 2.5 seconds and then passed again at 4 seconds. So it's gone past A and then come back. Okay, part B. Find the value of t when the particle returns to O. So it's gone away and it's come back. So we know the initial velocity is 13 metres per second. We know the acceleration is negative 4 metres per second squared. We're trying to work out t. What else do we know? At the moment we don't know the velocity it's come back at. But if it's returned to where it started, our displacement is 0 metres because it hasn't actually gone anywhere from where it started. It's in exactly the same place, displacement-wise, from where it started. It has not displaced any further, so therefore displacement is 0. So S equals ut plus half at squared. 0 is equal to 13t minus 2t squared. Now this one I'm actually just going to factorise. So t isn't equal to 0 because we're finding when it returns to O, that's when it first left O. So 0 is equal to 13 minus 2t. So therefore t is equal to 6.5 seconds. So remembering that displacement is different to distance, that's the key for a lot of these problems. And if you don't remember that, then it does cause issue for solving ones further along. Okay, example number 5. Obviously, when you're doing these, you might want to pause the video as you're going along to write these down and make sure you've got the right information. A car moves from traffic lights along a straight road with constant acceleration. The car starts at rest at the traffic lights. So at rest, meter speed is 0. And 30 seconds later, the car passes a speed trap where it is registered at travelling at 45 kilometres per hour. Find the acceleration of the car. Right. What is wrong with this? Well, we've got it in kilometres per hour. We need to calculate things in our SI units. So this was done in chapter 8. So we need to convert it on metres per second. So 45 kilometres per hour. So 45 kilometres is 45,000 metres over 3,600 seconds. So it's actually 12.5 metres per second. Now we've got that, we can work out our problem. So U is 0 metres per second. V is 12.5 metres per second. T is 30 seconds. And we want to find the acceleration of the car. So V, U, A and T, easy. V equals U plus AT, lovely. So 12.5 is equal to 0 plus 30A. So therefore A, 12.5 divided by 30 is 0.417 metres per second squared. I didn't write 3 significant figures in my notes, so I therefore assume that's exact. If not, then slapped wrist for not writing 3SF. Find the distance between the traffic lights and the speed trap. So in the question, I know U is 0 metres per second, V is 12.5 metres per second, I know T is 30 seconds, so what is S? So S is U plus V over 2T. So S is 0 plus 12.5 over 2 times by 30, which is 187.5 metres. Excellent. So the only difficult thing about that question really was making sure we are in appropriate units. We're always dealing with those SI units. Okay, final example. Use this pink. A particle is moving on the x-axis with constant deceleration. I'm going to write my acceleration to the side because I know what the drawing is going to look like. Obviously, you'd add it on afterwards. With constant deceleration of 2.5 metres per second squared, so negative 2.5. At the time t equals 0, the particle passes through the origin, moving in the positive direction of x with a speed of 15 metres per second. Find the time between the instant when P first passes through O and the instant when it returns to O. So we know it's going to come back and repass through O. So at time t equals 0, the particle passes through the origin O. So the time between the instant when P first passes through O and when it returns to O is simply how long did it take to return to O. The reason it's worded in that way is because sometimes the particle won't pass through O to start with, and it might just say the particle passes through the origin, moving in the positive x direction, blah, blah, blah. So it might actually pass through the origin at 1 second, at 2 seconds, at 3 seconds. So that's why it's worded in that way, but obviously the question tells you it passes through at time equals O. But you can see how we'd solve that problem anyway. So our initial velocity is 15 metres per second. Our acceleration is a deceleration, negative 2.5 metres per second squared. We've returned to the origin, so our displacement is 0, and we are calculating time. So S equals ut plus half a t squared. Remember, I've still got my formulae. They're just here, ready if I need them. So 0 is equal to 15t minus 5 over 4t squared. So t is 15 minus 5 over 4t. So this is where we might find actually we can't factorise it, so it doesn't pass the origin at t equals 0. It might pass at a different point if we couldn't factorise this in this way to have a value of t equals 0. So 0 is 15 minus 5 over 4t, and therefore t is 12 seconds. So it takes 12 seconds to return to that point. Part B. Find the total distance travelled by P during this time. So we know that P has gone out and then back again. So for the total distance, we need to work out how far out it's gone and then how far back it's gone. Although I have drawn it with a curve, it's travelling along an axis. It's just that I can't draw travelling along itself and actually have things going really clearly. So effectively this distance is 0. It's just we've drawn it so that it's easier to draw. So what I need to find is the displacement for when it turns around. So I've got to think about what I know. So I know that my initial velocity is 15 metres per second. I know that my deceleration is negative 2.5 metres per second squared. I cannot assume that this distance, the time it's taken to turn around is the same it's taken to travel back. That is not an assumption that we can make, because it depends what speed it starts at. It depends on the acceleration rate. If that was a much slower deceleration, that was a lower time. It's not equal. We cannot assume that. So we've got to think about some other information here, because I'm working out S and I don't know T. If it has changed direction, then I know that the velocity at the point it changes direction is 0. Because when something changes direction, the point at which it changes direction, velocity is 0. It's instantaneously at rest. So I've got V, U, A and S. V squared equals U squared plus 2AS. So 0 is equal to 15 squared minus 5S. So 2 times negative 2.5 minus 5S. So 5S is equal to 225. So therefore S is 45 metres. That is not my final answer. That is the displacement from 0 to the point it turns around. So therefore the total distance travelled is twice that, because it's gone there and back, which is 90 metres. So with these problems, you've got a few bits of information that are really important. Drawing diagrams are really helpful, and actually writing out your letters, writing out your equations, thinking about what you know and what you need to know is really, really vital with these problems. So I'll set you some work on online for you to be doing, and you can practice that in today's lesson and part of tomorrow's lesson outside of your live chat with your teacher.